Good morning, everybody. My name is Dan Lathrop at the University of Maryland, and I'm going to be talking to you today about reservoir computing, prediction, and high-speed hardware accelerators. So I'll go ahead and share my screen for the slides. So I'm going to tell you a couple things about activities that happen in the University of Maryland's theory group, but I recommend Ed Ott's talk also on that. So it's been a pleasure to collaborate with Ed Ott, J.D. Pathak, Michelle Gervin, and Brian Hunt on the theory side. And on the high-speed hardware accelerators, the experimental team includes Heidi Komkoff, Itamar Shani, Liam Shaughnessy, Artur Prevolov's been doing some turbulence prediction, and John Raza. And I'd like to acknowledge funding from the Laboratory for Telecommunication Sciences, State of Maryland, and the National Science Foundation. Oops. So much of the machine learning that's done in software is done on feed-forward neural networks, so called deep learning, where the nodes are nonlinear elements such as tanh functions and input data, for instance, such as a small handwritten image of a number 3, goes into an input layer, and then there are multiple hidden layers with weights adjusted between them. And the trained result in this particular case would be a classifier indicating that this handwritten number 3 is in fact a number 3. And the training is often done by backpropagation, and it's computationally highly intensive to train. So many of you are familiar with reservoir computing. Reservoir computing is a different way of setting up a neuromorphic network in as much as there are feedback loops. So down in the lower right here, so we would have also nonlinear nodes, large number of nonlinear nodes, but in a real general digraph that includes feedback loops and a certain amount of memory. Still, there's input data that comes in, fanned out by an input vector. Then that information circulates in the reservoir, and the desired output is then trained by only modifying W out, an output matrix. And I'll give a little bit more detail on that. So reservoir computing as a machine learning tool was independently introduced by Jaeger and Moss. And the main component, again, is this high dimensional reservoir. So think thousands of nodes in a loopy graph. So the reservoir provides an ability to have a wide variety of dynamics that it can exhibit. And in addition to being able to have software models, such as our group uses Python models or MATLAB models, these reservoirs can also be implemented in real physical systems. Some groups have done it in photonic systems or electronics, and we're using arrays of logic gates, field programmable gate arrays, to also implement the reservoir computer. So the demonstrated uses are quite varied for reservoir computing, including time series prediction in economics, control in robotics, signal rate improvement, noise reduction and nonlinear correction in communications, and we'll come back to that use case. Speech recognition, including one of the systems that had an optical system that they set up to do speech recognition. Image classification of the handwritten digits that I showed on the second slide, and we'll come back to that use case as well. And in medicine, real-time detection of seizures. And then this last example is from the Maryland Theory Group, the prediction of chaotic and turbulent time series, and actually using the reservoir to even characterize those time series. So again, the main component of reservoir computing is this high-dimensional graph of nonlinear nodes. The state of the graph then is given by this vector R of t. So R has just a single real number at each node, and over time then that information is processed nonlinearly and fed forward to other nodes in the graph. The connectivity of the graph is specified by an adjacency matrix A, and generally these graphs are sparse, often randomly generated, and are fixed during training. So there's nothing about the reservoir that actually changes during the training. Now, while I say that the graphs are randomly generated, that's going to be the case for most of the work I'm going to show you today. We also have developed genetic algorithm methods for improving the networks in our electronic examples. So I'll come back to that late in the talk. So the software models then that are used in dynamical systems will take some input signal, U of t here, let's say a time series out of a Lorentz model or some turbulence data, feed it and fan it out into the reservoir. It circulates in the reservoir by this formula in the middle left here. So there's a tanh function that controls the output. That tanh acts on the reservoir vector R, fed forward to other nodes by the adjacency matrix A, and then external data is fanned out onto the network by an input vector Wn times the input data U. And then that just takes us one time step forward as information circulates. So during the training phase, the input data is fed in and the R of t is then observed over time. And we will implement some sort of cost function or error function shown here below, where for some length of time, minus t up to 0, we're just going to observe the state of the network and compare it to, or actually develop and fit W out so that the W out times R of t successfully models U of t at the next time step. And so then at that point, we have a system that is just a time stepper that you give it the state up to a certain point, and it will tell you what the next state of the system is going to be. Then in a prediction test at time t equals 0, one can then just start feeding in the output back into the input, and now you have a ability to predict forward in time, and you now have just developed a mimic or a model of the original dynamical system, capable of prediction or even capable of mimicking the original system. So let's look at an example of that. So the example that I was greatly impressed by was JDeep's work on the Kuramoto-Sivashinsky equation, where they simulated numerically this partial nonlinear differential equation and developed then this weak turbulent time series over time. This is a classic model of weak turbulence. It has a periodic domain L, and the size of the domain L also can control the complexity of the system. So for instance, the Kaplan-York dimension can be varied from, let's say, 23 at L equal 100 into the hundreds, 1600. So this is a high dimensional system. So then we go in with the reservoir and train it on some data from some minus t to 0, and then at time t equals 0, we go forward and just have the reservoir compute the future of that time series. So that's shown in the middle panel. The actual data that the reservoir did not have access to is the true state starting at t equals 0. And to start with, they compare quite favorably. So the difference between those two images is shown at the bottom. So on the order of 4 or 5 Lyapunov times, the reservoir is able to do an accurate prediction of this weak turbulent state. But not only that, after that Lyapunov time of 4 or 5, it still computes something that looks similar to Kuramoto-Sivashinsky data. Not just that, but you can go in and query the reservoir for various measures of the character of that turbulence, and that's what the theory group showed here, is that you can actually go measure the Lyapunov exponents of the reservoir-based system, and those Lyapunov exponents compare favorably with the Lyapunov exponents of the original system, not just the positive exponents associated with the growth of error, but the negative exponents as well. And this is one of the more impressive results that I'd seen in a long time, and one of the reasons why the experimental group decided that we would go in and try out the reservoir computing on both some turbulence data, and then think about how we could build reservoir computers as real physical systems. So that will be the next example I want to show, is where we're going to do attempt the same sort of reservoir computer prediction task, but on turbulence data from a laboratory experiment. So this laboratory experiment is simulating spherical wet flow. And so there's an outer sphere, a liquid in between an outer and inner sphere, and the two spheres independently rotate. The Reynolds number for this system is on the order of 100 million, so a strongly nonlinear system. We measure time series of the experiment of the magnetic field at 33 locations. So this is a liquid metal experiment, and the magnetic field is participating in the turbulent dynamics. And then we do a reservoir prediction on that 33 vector of input data. So it's a real physical system. So some of you know I have a 3-meter diameter laboratory model of the Earth's core in my lab. Has 12.5 tons of metallic sodium in it. And we're going to focus on of the variety of sensors, just the Hall probes, 31 of them that are on the outside of the sphere and 2 of them that are on the inside of the sphere. So yeah, it's a real physical experiment meant as a model of the Earth's liquid outer core, which is responsible for generating the Earth's magnetic field. Here's a picture of the system on the right. So the sphere you see is inside of a stainless steel cube that forms a structure for all that rotating equipment. And Dan Zimmerman shown up top. He was one of the original researchers that did a lot of the design and build with Santiago Triana of this experiment. So Arthur Prevloff, then one of the current grad students on the project, then working with Brian Hunt and I, have shown the ability to do prediction on the magnetic fields. Again, the basic notion is we train the system by letting it observe a large amount of Hall probe data and then start predicting here at t=0. This is just one of the 33 probes that we predict. It's kind of hard to look at all 33 in the same graph, but you can see that there is a relatively accurate prediction in early times, blue being the true state of the magnetic field coming out of the system, and red being the reservoir computer prediction. So the top panel shows the first 10 rotations. The middle panel then is rotations 100 through 109, where you can see that the reservoir is still predicting the waves in the system, the large scale MHD waves, but has stopped predicting or accurately predicting the small scale turbulence as it did in the top panel. And then in the bottom panel, rotations 260 through 270, the waves are still present in the reservoir computer prediction, but they've become out of phase with the experimental data. Another way of looking at that data is to actually take all of the 31 probes on the outside and form a map of the magnetic field. So here, again, we start prediction at time t=0, and I'm showing maps of the magnetic field at 27 rotations into the data, which is on the order of 2¼ magnetic dipole diffusion timescales. So the top map shows the radial component of the magnetic field, where blue is outward pointing and red is inward pointing, mapped onto an equal area projection on the outer sphere. The bottom map shows the reservoir computer prediction at that same time. And you can see that the map is relatively accurate. And so the reservoir is doing something like predicting the magnetic field weather coming out of the experiment. So, I want to turn now for the rest of the talk to discussing how we can use nonlinear dynamical systems, high-dimensional systems as reservoirs to do machine learning tasks. And the motivation for going from a software model or computer model to a real physical system as the reservoir is the difficulties that machine learning has, and in particular, the energy costs of machine learning is staggering. So it's estimated that the US data centers doing machine learning, think all of the large internet providers that place ads and search for you, consume about 70 billion kilowatt hours in 2014, and that's estimated to reach as high as 140 billion kilowatt hours in 2020. This is because these server farms are just having a vast amount of computing power and GPUs and all churning away at the machine learning. The results are quite impressive, but the costs are quite high. And the thing about paying for computer power is that you actually end up paying twice in some sense. You pay to power the computers, and then you pay to cool the computers themselves and the buildings that they're in. Now, the other problem that machine learning has in many applications is that it is generally connectivity dependent. So when you have voice recognition tools, let's say in your car or on a device on your shelf, or when you do searching, those are all then sending those queries via the internet back to cloud servers and then returning the result. That there's some local machine learning that's done, but the majority of it is done remotely, and so it lacks a certain robust local performance. And this is mainly because if you're using battery powered devices, the draw would be so great if you did local machine learning that it's not practical. So the notion is that if we can come up with a way of reducing the energy costs of a local device that would have many applications. And the basic proposition then is that we can develop high-speed hardware accelerators that would locally be able to do reservoir computing. And there's, of course, a long history of high-speed hardware accelerators from math coprocessors back in the 80s through to the current use of graphical processing units, GPUs, both in graphics and in now general computation. Field programmable gate arrays are also used in modern computation, a little bit less known as GPUs. And what we're going to show is that one can take a field programmable gate array and configure it in a way to change its personality to become a reservoir computer, and something that we're calling a reservoir processing unit. So the idea of making a physical system hardware accelerator for reservoir is something that a number of groups have exploited. And the basic notion is that a nonlinear element that's used in the software, let's say a tanh function, can be used as a nonlinear element in some other physical system. People have demonstrated electronic circuits with transistors, optoelectronic systems using Mach-Zehnder nonlinearities. I think that even a stirred bucket of water was used for a reservoir computer. So a wide variety of nonlinear systems can be used. And Dan Gauthier is also giving a talk at this workshop, and I recommend that you look at his talk also on FPGA work. And we've collaborated some, and I found his work very interesting and inspirational. And we went forward to look at how we could use logic gates as nonlinear elements in doing reservoir computing. And the basic motivation for that is that if you look at a logic gate as a purely binary thing, then it just does a Boolean logic in a way that enables computation. But if you look at the actual voltage transfer functions for a logic gate, here's one shown for a NOT gate, the voltage out versus the voltage in looks something quite like a tanh function, flipped over and shifted, but it's a nonlinear transfer function that at the extremes, if you input a 0, you output a 1. If you input a 1, you output a 0. So it does logical processing at the endpoints. But if you use the voltage as a real number instead of just binary, it carries more information and will be nonlinearly transformed by the gates. Of course, a NOT gate is just a one-input device. We use 2, 3, and 4 input logic gates that have higher dimensional transfer functions, but they're all doing some sort of nonlinear transformation on the data. Now, the field programmable gate arrays allow us to build very large arrays of logic gates in real general graphs. So the field programmable gate arrays, or FPGAs from here out, have hundreds of thousands of activation units, even up to millions now. They have programmable hardware interconnects, so this allows us to configure graphs of our own design with logic gates of our own choosing. And if we run these in an unclocked way, the response time of the nonlinear element is simply the propagation delay through the gate on the order of 100 picoseconds. So all of the gates are operating in parallel and updating in real time in a nonlinear unclocked system of gates. So we can implement this on commercially available FPGAs. Here's a Xilinx Zinc chipset on a commercially available development board. So this is the pink Z1. So it's actually an educational, in this case, intended FPGA development board. And we've been able to implement then large arrays of gates, think thousands of gates, into reservoirs on these FPGAs. And also a Python handle to allow us to send data into the logic fabric and retrieve the state of the logic fabric back out again. So this PyRPU package we developed just allows us to communicate with the logic fabric, and overall allows us to generate these RPUs. So we're going to go forward and look at the overall the overall performance of a large number of logic gates in the system. And to start with, we're just going to build a 501 note array of 2 input logic gates on the FPGA. So this is originally work of Itamar Shani in my group. Just to see what would happen, we went ahead and made all of the logic gates exclusive ORs, XORs. So they're 2 input devices, so there are 102 total connections, so 0.4% connectivity, so a large, sparse, random matrix. And we went ahead and just developed a random adjacency matrix and used that to produce a hardware description language that the FPGA could use to reconfigure itself internally. So again, it's asynchronous updates on this, so there are no clocks, and there's just information freely circulating on this large graph of nonlinear elements. Now, in this particular case, we didn't put any input on the reservoir. We were just curious and interested on what would be the dynamics of the reservoir freely running with no input data. And this was really just with a mindfulness of what we've seen in the past, where arrays of logic gates can have autonomous dynamics of their own. And this network very definitely did that. When we powered it up, these 501 XOR gates just came to life, circulating large amounts of what I'm going to call spatiotemporal turbulence within this graph at picosecond time scale, so or 100 picosecond time scale. So we have sort of gigahertz class turbulence. These graphs show a particular node update, and we just have shown 5 time series examples. All of the nodes are executing similar behavior out of this graph. Now, I just want to point out that this is not a very useful reservoir computer because it's freely generating turbulence with no input. It's an overexcited system, and that's something that we will have to get a handle on in order to make real useful reservoir computers. Now, the realization of the XOR was a kind of inopportune choice is that in an XOR gate, any possible change of the input pins always leads to a change in the output. So for instance, if the input is 1, 1 on this graph, the output is 0. If I change either of those inputs left or right to 1, the output changes to a 1. And that's true for all 4 possible input states. No matter which pin you change, if you change one input, it changes the output. So we're going to call this a sensitivity 1. It's the maximum sensitivity as compared to other logic gate types. So for instance, in an OR gate, there are 3 states that output 1s. The input can be 1, 0, 0, 1, or 1, 1, and output a 1. Only 0, 0 outputs a 0. But in this 1, 1 state, I can change either input and the output doesn't change. So the OR gate, also the AND gate, and other gate types are less sensitive than the XOR gate. In this particular case, they have a sensitivity of 1/2. And this definition can be generalized to 3 input gates or 4 input gates, and you can go forward to just measure the sensitivity. So what we're going to do is, now that we have a measure of the sensitivity of the gate, we realize that the XOR gate, being the most sensitive, was generating a large amount of turbulence effectively because of this oversensitivity. So we're going to look and control the average sensitivity of the network as a way of controlling the self-activity. So what we find is that if the average sensitivity is close to 1, we get turbulence. As we turn down the average sensitivity by mixing in AND gates or OR gates, or even pass-through gates with a sensitivity of 0, we go from turbulent to spiky, eventually to quiescent behavior. So this lower right graph shows the average sensitivity of a network. As we reduce it, then we go from, what's plotted here is the activity level of 15 randomly sampled nodes. So the activity level is quite high at large sensitivity. Things become spiky at sensitivities around 0.5 or 0.6. And I know that there is interest in spiky neuronal computation. There may be some opportunities for research here. And then below about 0.55 for this particular network set, the system goes quiescent. Now, this is a reservoir with no input data, and so one might want a useful, computationally useful reservoir to be quiescent until you present it with input data and then become active. And this is reminiscent of things that are known about neuronal systems in mammalian cells. The work of Dietmar Plenz has shown that a healthy neuronal system is sort of poised in a critical state between being overactive, which I would say these turbulent states are, and being underactive or a depressed state, that at low sensitivities we have, and that useful computation may take place in this middle point, as well as possibly a longer periods of time where information circulates within the network. And we'll look at that in a little bit more detail. So here's in another study Liam Shaughnessy did with a self-activity in a large network or large number of different random networks as a function of the mean sensitivity. And again, we see at low sensitivities, low self-activity. And as we pass through around 0.5, the self-activity level jumps up notably. Now, I want to point out there's a fairly large scatter when you randomly generate different reservoirs. Some will be more active and some less active. And that's something we'll come back to and discuss a little bit later. Another set of tests that we did, starting with Ademar Shani and then Liam Shaughnessy following up, were pulse tests, where we applied a single input pulse. Now that we've sort of got a handle on the reservoir behavior with no input, now we're just going to send a pulse input and look at the response. And what we see is, depending on the reservoir configuration, input pulses may rapidly die down, as in case A. At the top here, they may have a long transient returning to the original state in the middle case. And there are also other reservoirs where a pulse sends it on a transient, but then the reservoir returns to a different state than it was before. So short and long transients, and then convergent or divergent responses, depending on various aspects of the reservoir design, including gate type and sensitivity. So, we also did tests on hundreds of reservoir designs in FPGAs, looking at the transient length as measured and observed in clock cycles. So the reservoir is running unclocked, but our observations of it are clocked. Again, as a function of the mean sensitivity, we have transients that then tend to peak in this middle zone around a mean sensitivity of 0.5. So actually, just going back to this, so one of the things that one can observe here is that given a large collection of randomly generated reservoirs, there's a range of transient lengths that are observed from short to quite long, just given the different adjacency matrices and the different list of gate types that are used. Now, having observed that, we started to wonder whether or not we could select reservoirs that had better or more optimal performance than others. And so we did a preliminary study using genetic algorithms to tune the reservoir type, in this case, to optimize to have a transient length of 50 clock cycles. So in this particular study then, we had 200 randomly generated reservoirs. This is 300 node networks. We pulsed the networks and then observed the transient length. And then we picked the best 5% of this 200 networks that were having a transient length of our choosing. And then we took that 5% and used a genetic mix of that 5% to produce another population of 200, putting in some random mutations as well at the 4% level. And you can see that after just a few generations, we are able to get the transient lengths on average to converge to about 30 clock steps, and the top tier end up being spot on at 50 time steps. So we're going forward to look at how we can also use genetic algorithms to evolve reservoirs on different machine learning applications, where instead of a transient length being the optimization, accuracy can be, but that's something that we're just starting to ramp up to. Now, I want to show several use cases then of these reservoirs and the FPGAs doing machine learning tasks and how they performed on that. The first few are going to be use cases that were already existing in the literature, and so we just took reservoir computing tasks that have been demonstrated in software models and just tried them out on the FPGA-based RPU. The first one we did was a machine learning task of cleaning incoming serial data. The data then has nonlinear distortions and signal loss, so that is noise that is added into it. And we trained the FPGA then to reduce the distortion and noise for a recovered serial signal, and we do that on a large sample of distorted signal where we know what the recovered signal looks like, to then compute the output vector, and then we test it on a variety of incoming distorted data where it was not part of the training data. And we were able to demonstrate a signal to noise and distortion recovery rate of 800 million bits per second on the reservoir, again, because of the very high speed that these FPGAs operate at. And I guess I didn't have a graph here, but we also looked at how that depended on signal to noise degradation as well. The second use case that I want to show is one that I mentioned at the very start of the talk, which is image classification. So a very standard kind of a baby introductory machine learning task is the MNIST handwritten image database. So there are 10,000 handwritten images. And the basic notion being that a reservoir can be fed the image into it, and you can train it then just to produce a binary vector classifier on the output. So we did this on a Xilinx Vertex 7 FPGA dev board shown here. We used a 4096 node reservoir. This particular chipset had a 250 megahertz clock. And we were able to demonstrate the ability to, at 94% accuracy, classify MNIST images at 20 million frames per second, using about 2.8 watts on the chip for an overall 7.1 million frames per second per watt. So just a little bit deeper about how the data flow happened for this particular case. We took the MNIST images and we thresholded them into binary images. So here's an example of a handwritten number 3. We took the 2D image and we unrolled it into a 1D binary vector, so about the 700 long vector. And then that binary vector is fed, the 700 binary vector is fed into a 4096, or in this case, I think this is an 1800 node reservoir. We then allow the reservoir to do its nonlinear computation on it and observe the reservoir state after 1 or 2 clock cycles. That then is trained, there's an output vector then that would multiply on that to produce the classifier. So here's a comparison of our RPU tests at the bottom on the MNIST data set to other FPGA-based MNIST classifications. These other ones were not using reservoir computing, but we're using other sorts of conventional compute algorithms, but instantiated on the same types of hardware. So our speed is actually quite a bit higher than any of these other conventional compute diagnostics. Our power is better than all but one, although if you can see our error rate is to suffer, we get maybe a 1% higher error rate than, well, 1 to 3% higher than the other use cases. So we also went forward and did a study where we looked at how the mean sensitivity of the reservoirs affected classification accuracy. And what we saw in this particular study, trying out hundreds of reservoirs, is that the lower sensitivity reservoirs for this particular image classification did better than around half or higher. And I think the basic notion is this image classification is not time series data, so you really don't necessarily want memory. You want to just do a logical computation on the image data set, project it up to the high dimensional data set, and then project it back down with the output vector to give the best possible accuracy. So the next use case that I want to talk about is not one that had been tried before in the software models, but one that we tried out based on the notion that the reservoir should be good at time series classification. We tried out the basic case of classifying radio frequency transmitters. So of course we have RF transmission happening all over the place, be they handheld radios or cell phones or Wi-Fi communications or all sorts of RF around us. And it's known that RF classification is needed for a wide variety of things just to determine what are open channels. But in our particular case, we're also going to look at whether or not we can classify radio frequency transmitters between different transmitters that may be the same make and model. but just different individual units. So we obtained a data set from the Laboratory of Telecommunication Sciences that had 31,000 transmission bursts from 5 different transmitters that we're going to label 0, 1, 2, 3, and A. All of these transmitters are actually Wi-Fi transmitters, all transmitting on the standard IEEE Wi-Fi standard 803.11. And so basically then we take these bursts that are a complex signal, we need to encode them, and we're going to use a phase difference encoding that I'll detail in a minute. We then feed those as time series into the RPU in the FPGA logic fabric. We then compute an output vector, and then that produces a binary vector one-hot classification. So, in practice, what we did was actually take from these radio bursts just the very first part of the burst. So an example burst then is shown in the middle right here. There tends to be in all of these transmissions a preamble, a modulation sampling, and then a data packet. And so those of you that can remember old-fashioned modems probably have heard similar things happening where there would be a hum and then a chirp and then data coming through. Those of you that have not heard it are younger than some of the rest of us. We were able to demonstrate 7% accuracy with no additive noise on these. And then as we added noise, degradation that occurs. And when I say 97%, that's actually for the best transmitter. If you look at all the transmitters, we actually have a different performance depending on the individual transmitter. I'll detail that in just a minute. So the encoding and pre-processing of data is often important in various machine learning tasks. And in our case, we actually tried a variety of different encodings on the radio frequency data before finding one that seemed to outperform the others. So I'll describe how we encoded it. To start with, the time traces are complex time traces, which is standard for radio frequency. So there's a real part that is in phase with the transmission frequency. There's a quadrature signal, the imaginary part, which is 90 degrees out of phase of that. And both the real and imaginary parts carry information in what is usually referred to in RF literature as in phase and quadrature or IQ signals, but it really is just a complex time series. What we found is that if we first computed the complex phase of the signal, so now we have phase as a function of time, and then computed the forward difference of that complex phase, that gave us a useful pre-processing that allowed the distinction between different processors or different transmitters. And so we take that time series then of the forward difference of the phase and render that into a binary image that then we're going to feed into the RPU for classification. So here's what that literally looks like. So I showed on the previous slide then what the binary image looks like we're going to feed in. So we feed that into the RPU, and then we observe the state of the RPU while it is observing that image, and that's shown in this image here that's labeled R. So this is the state of the reservoir as a function of time while we're feeding in the radio frequency signal. We then compute the output vector here labeled as a W that gives us the best possible accuracy to produce a classification. Here we're calling that T. And so since we know what the desired T is and we know what the state of R is, this is really just done using standard regularized least squares, which is essentially inverting the covariance matrix of R, comparing that to R prime times T to get the best linear output vector W. So that you can see the formula for that here on the left-hand side. So in the end, these 4 or 5 different transmitters have very different classification accuracies. Actually, transmitter 0, we essentially, with no noise, can accurately identify it 100% of the time. Similarly, transmitter A, we can identify it about 98% of the time. But we have difficulties with transmitters 1, 2, and 3. And I should point out that transmitters 0, 1, 2, and 3 are actually the same make and model of transmitter, just different physical systems. So we're actually trying to distinguish between what are nominally identical manufactured devices. Of course, whenever you manufacture two things, there are always differences, slight differences, let's say in frequency or the nonlinearities of the transmitters. And so they're each going to have their own voice, if you will, that allows classification. So this is a confusion matrix of what was the actual transmitter, what did it classify as, and transmitter 2 then really ended up being kind of our downfall, only accurately classifying 49% of the time. Transmitter 2 apparently likes to masquerade as transmitter 0, and so then that led to a significant overall degradation in accuracy. So, and on the right here then, we just show how, as you put in more training samples, how the testing accuracy improves over time. So after a few thousand samples, we're already getting fairly high accuracy for the most accurate transmitters. So, so let me talk a little bit about a roadmap as we move forward. So, you know, where we're at now in looking at the machine learning hardware is being able to put these RPUs into commercially available FPGAs and commercially available chipsets. And we've demonstrated then use cases in various ways for that. We're going to go forward to test more of those. We also then are interested in whether our own chipsets of our own designs could be used for reservoir computing. So Heidi Komkoff in our group has designed a half a dozen different integrated circuits that we've had made in a collaboration with NIST as application-specific integrated circuits. So those were actually fabricated this year in 2020 and have been shipped to NIST pending cutting them up into the different groups that are getting different parts of the chipsets. So the basic notion is that we can make our own chips that have reservoir computers on them. We can feed analog signals, let's say generated by an arbitrary waveform generator, into those chipsets and then observe the state of the reservoir, either digitally or using high-speed oscilloscopes to observe the analog state of the reservoir overall. So that's upcoming research that we're working on. So a couple of aspects. The FPGA work continues, especially as there are different generations of different speeds of the commercially available FPGAs. So most of what I've shown you today is in 7 series Xilinx FPGAs at 28 nanometers and on the order of 200 megahertz clocks. They have 2 additional generations following up that, the UltraScale and the UltraScale Plus generations, now with clock speeds up at 600 or 700 megahertz. And so those directly lead to direct speed-ups of the overall machine learning use cases as we go to those further generations. So we're now doing experiments on the UltraScale Plus logic MP-SOC hardware. The ASIC implementation then is something that we look forward to removing some of the limitations that the FPGA places. That is that the input data and the output data on FPGAs always come in as strictly binarized, where the reservoirs could in principle take non-binary input, like direct RF input into a circuit. And so then that's something that we should be able to try by feeding things like RF signals or even things like chaotic signals directly into an ASIC for machine learning tasks. So in conclusion then, reservoir computers allow surprising capabilities to predict and characterize time domain signals in chaotic, weakly turbulent, or experimentally turbulent data. We've demonstrated unconventional FPGA reservoir computers just using CMOS logic gates in both inference and data cleaning. We've been able to instantiate 500 to 4,000 node CMOS logic gate recurrent neural networks in commercially available chips. I want to highlight one of the publications of the theory group. Again, Ed Ott is the last author on that 2018 paper, Model-Free Prediction of a Large Spatio-Temporally Chaotic System from Data, Reservoir Computing Approach. And then on the hardware side, then we have 2 2019 publications, Dynamics of Analog Logic Gate Networks for Machine Learning, that appeared in the journal Chaos, and an archive preprint, the Recurrent Processing Unit Hardware for High-Speed Machine Learning. So, and I look forward to seeing questions in the question section for this workshop, and look forward to seeing you all in real time in some later year. Have a good day.